Hello, in this short video I'm going to introduce you what are the Quasi-Newton methods. So if you remember in Newton-Raphson methods, we need to compute a Jacobian matrix and then we need to compute the inverse of the Jacobian matrix. In system of equations that they are very large, this inverse and this evaluation of the Jacobian matrix can be very time demanding. So the overall idea is just to replace this Jacobian that we call J by something else. So this is a matrix which is evaluated at this particular iteration U. In general, this matrix has the size of the Jacobian, of course, but is not necessarily the Jacobian. So what can we replace in that to have a relative good performance of these Newton-Raphson methods? Well, the first idea is what is called dishonest Newton methods. It's just to keep the Jacobian of the previous iterations for maybe 3, 4, 5 iterations. The overall idea is to use the Jacobian for k iterations. So the definition of the Jacobian will be the same for k iterations. So you can imagine this Jacobian is representing kind of direction of search. So this is basically where you update the value in new plus 1 by the previous value, and this is an updating part. While this updating part is trying to look at the direction of making this set of constraints equals to 0. Probably if the Jacobian doesn't change too much from one iteration to another, so it could be enough for keeping the same Jacobian for a fifth iteration. That you can do is like, well, start iteration number 1, so you compute Jacobian. I will put like this for the iteration number 1. Iteration number 2, you compute another Jacobian related with iteration number 2, and then the next, let's say k iteration, let's say k is equal to 3, so 3, 4, and 5, I will keep using the Jacobian of 2. And then in the sixth iteration, so I compute a new Jacobian related with this point value. So it's important to understand, like for the very first iterations, usually Jacobian change more than the last iterations. So we can have some adaptive update of this Jacobian. So this is the previous example. If you remember, we have this function that it's like this, f of x, this is x. And this was the analytical form of every step for the Newton-Raphson method. Basically what we do here is just to keep the Jacobian for a few iterations, and then overall idea is just, well, you will see we need more iteration than in the previous case. This Jacobian, it's form of partial derivatives. So the idea is, well, why not approach these derivatives using numerical methods? So imagine that you have a function, whatever is your function, and then this is fi, and this is the component xj. This is the pen of xj. Or if you want to think about just one-dimensional function, this is fx and this is x. So the idea, it's just how we can approach, let's say, derivative in a particular point, this iteration new. And what we can do is, well, let's create a perturbation around here. This perturbation usually is plus delta x minus delta x, and then use the value of this function in this point and this value of this function in this point. I can have this as the derivative around this particular value. This is not derivative evaluated in here, but this is just a numerical approach using this perturbation. In general, this is very cheap for calculating that, because evaluation of function is cheap. And this is a constant number, which is probably a parameter of our algorithm input. Well, another way of computing this derivative is using the secant method. So the secant method will take advantage of the values that we have already explored in the previous iterations. So let's imagine that, well, we are here in this iteration x0. We will have already a evaluation here, this point of f of 0, which is f0 is equal to f evaluated in x0. Then let's assume we also know what is this value, x1, in this iteration 1. Again, we can compute approximation of how looks like this derivative, and we can use this for iteration number 2. So basically this is what I have here. Yes, the difference with the previous method, numerical approach, is like this delta actually is adaptive. It depends on each iteration. As we go farther and farther, this difference between one point and the next one is decreasing. So we are finding approximation of this derivative more accurate in the local point of evaluation. This is for one dimensional, but this can be extended for multidimensional problems.